Royal Institution Christmas Lectures, Waves and Music, Lecture 5. 20 seconds. Ten, 9, 8, 7, 6, 5, 4, 3.
I must apologize for walking in like a crab. Had a slight catastrophe yesterday, got squashed between two cars. Actually, they were a day early because we're not talking about catastrophe theory until the next lecture. Today, we're going to talk about waves and music. And I want to start with a nice simple instrument, the Brazilian berimbau. As you can see, it's just a piece of wire strung on a bit of wood, and there's a bit of string here attaching a gourd which acts as a sounding box. And you play it like this. Only I should explain, of course, it's at the moment it's summer in Brazil, and so I'd have a bare chest, and I'd be doing that, and it'd go boing against my chest, so I can't do it properly. And I should also explain, this is part of the Brazilian version of Kung Fu. They call it capoeira, and the training of it, they have schools in which they make the training into a dance. And this is a very elegant, slow dance, handstands, and all of a sudden, the foot of one of the men goes within half an inch of the other one. And usually, and the dance is always accompanied by music, and very often the music starts with two of these berimbaums opposite one another. So we'll try it. Thanks. I should explain who the band is. Isabel is a mathematician from Brazil who's actually danced and played and fought in capoeira schools. And the other three are my children who've come in this lecture to help with some of the demonstrations, the more complicated ones. Well, I want to explain how this works, how when I bang this here, it actually makes a sound in your head. What happens when I bang it is a wave starts rushing along this wire at about 200 meters per second, which is about 450 miles an hour, and then well, it's a bit difficult to see, so I think we'll demonstrate on something that's similar, where you could actually see the wave. So I've got this nice long rope here, and so I'll send a wave to the other end of the rope and watch what happens to it. You see, it went up and then reflected back, went up and rang the bell, reflected back, went up, rang the bell. So I'll do it again. So it went, reflected back and forth. Well, in actual fact, you can work out how long it takes. See, if it goes about 200 meters per second, this is about a meter. So to go there and back is about 2 meters. And so it goes there and back in about 1/100th of a second. So every 100th of a second, the wave comes along and gives that piece of string a little jerk. And then the string gives the gourd a little jerk, and then the gourd gives the air a little jerk, and then the air goes out like an expanding sphere at 750 miles an hour till it reaches your eardrum, and then that gives your eardrum a little jerk, see? And that happens 100 times a second. So we call that number the frequency. So 100 times a second, your ear is jerked. Now, how does your ear manage to count 100 times a second? I mean, if I blow a whistle, it jerks your ear 2,000 times a second. And a really high note would jerk your ear maybe 10,000 times a second. And if I played a chord, it would be jerking your ear sort of at 2 different times a second at once. Now, how does the ear manage to count that? Well, the answer is the ear contains a resonator. So here we've got a resonator. Now, would anybody like to come out and operate this resonator? Okay, you haven't come before, have you? Come along then. So, you stand there. Now, what you're going to do is to set this pendulum swinging. I'm not trying to tell you that your ear contains this, contains a piece of string with lots of balls hanging from it. What your ear actually contains is a membrane with some hairs on. However, the principle by which your ear operates is the same as the principle of which this resonator operates. And therefore, by demonstrating this resonator, I can demonstrate the principle by which your ear operates. And so when we swing this red ball here like a pendulum, that's going to be like the music rattling your eardrum. What's your name? Catherine. We've had lots of Catherines, haven't we? Okay, Catherine. So that pendulum will be rattling your eardrum. Now, this bit of string in between here and here is like the 3 little bones in your ear, which translates the vibrations to a chamber full of liquid. And then this, in the liquid translates the vibrations to the membrane containing all the hairs. So that we've got to guess what's going to happen to all the hairs when we swing the pendulum. So you hold out that there very gently, and I want you to hold it very gently, let it go very gently. Hold it, and now I want you to let it go very gently so as to not wobble the machine very much. Ready? Go. Now, what's going to happen? The answer is you see, this is the only one which is actually picking up all the energy. All the others are still. You see, and that picks up, so what happens to the membrane inside your ear is that it picks up, only one of the hairs picks up the energy, and then the ringing of the bell symbolized that hair, because it was bent sufficiently far over, it sent a nerve impulse to the brain. So the brain registers the fact that only this hair is vibrating. So now we'll play a chord. So I'll put the other bell ready. I think that's it. So I'll play this one. You hold that one out, quite a good way out, and you're going to release it very, very gently when I say go. Ready, steady, go. This one's picking up again, you see. And the others don't swing very much. Thanks very much, Catherine. Well, when you're usually speaking or you hear the usual sounds of the world, then, of course, all the hairs are in operation most of the time. And when only one hair fires, the brain sits up and takes notice and says that's rather unusual. And if only 2 hairs fire, then the brain also takes note. And that's why musical notes are different from most other sounds and immediately recognizable. And it's probably why several species use musical notes to communicate, such as birds and whales. Well, I now want to go back and see if I can slow up this wave. And so we've got a special wave machine here which sends very slow waves. I want to see exactly what a wave looks like. This, would you like to take this one, Bill? This wave machine is made of lots of parallel bars which are pivoted, freely pivoted in the middle, and then a little bit off center there's an elastic piece of wire which is threaded through the bars. And therefore, if I pull up one bar, this pulls on the elastic and that pulls the next bar up. And so the movement is propagated along. So I'll do that now. I'll unloose the ends. And so you see a wave running along. If I send, it's coming back. So I'll send 2 this time. You see, we've slowed it up. Well, now, one curious thing is there's no actual matter going along. What is it that actually goes along? The bars themselves just go up and down. And so what goes along is actually a geometrical picture. It's an abstract thing. Therefore, the only way to describe waves is with mathematics, because it's an abstract thing that we have to capture. And since it's a continuous thing, behaving continuously, it's one of our 3rd types, or one of our 4th types of modeling, so we have to use calculus. Well, I'm not going to prove any theorems today. I'll just state them. So here's the first theorem. It says the speed of the wave is equal to the square root of the tension in the wire divided by the mass of the wire. Now, it's easy to see why, if you increase the tension in the wire, the wave would speed up. Because if you increase the tension, the tendency for each bar to pull up the next bar increases, and so it would speed up. Again, if you made the bars heavier, then they'd be a little bit slower to move up, and so that would slow the speed. So it's intuitively obvious that you'd have tension on the top and mass on the bottom. It's not quite so obvious why you'd have a square root here, but I'm not going to prove that. But what is astonishing is that the speed doesn't depend upon the shape of the wave or the size of the wave. Now, in water waves, it's quite different. Because if you think of the little ripples on the seashore, they run along very slowly. But if you think of the big Atlantic rollers, they go along quite fast. And if you think of the huge tsunami in the Pacific, they are waves which can travel at 400 miles an hour. They're only 6 inches high and tremendous long wavelength, but they travel right across the Pacific, and when they get to the other shore, they build up into a huge tidal wave and tend to swamp cities and seaside towns. So in water waves, the speed depends very much on the shape. But here, apparently, it doesn't. So we better test that experiment. So what I'll do is I'll send a little wave, then a big wave, and then a slow round one, and they should all go at the same speed. So watch carefully. Here's a little one, and then a big one, and then a slow round one. See, and they're all traveling along at exactly the same speed. And here they're all coming back, all at the same speed. Now, the next thing to test is the frequency. You see, you remember when I calculated the frequency of this, I took the speed, which was 200 meters per second, and I divided that by twice the length, which is 2 meters, and I got the frequency of 100. Well, so the frequency is the speed of the wave divided by twice the length of the wire, and then I can substitute for the speed what I had before, that square root of tension over mass. So my frequency is now 1 over twice the length multiplied by the square root of tension over the mass. And it doesn't depend on the shape. It doesn't depend on how I bang the instrument. For example, I bang it here, or I bang it here, or I pluck it. And so I get different shaped waves, but I still get the same note. See, because the frequency doesn't depend upon the shape at all. It's very convenient that it doesn't, otherwise we couldn't have stringed musical instruments. But now I must confirm that the frequency does depend on those three things. So the first thing we'll test is the tension. You see, what I'll do is I'll press this on the bench like that, and that'll increase the tension in the wire, so the note ought to go up. And if I turn it round and press the other way like that, that'll release the tension, so the note ought to go down. Now, the next thing to test, what's the next thing? The mass. Oh, yes. If we put a little mass on, I'll do that with a paper clip, maybe here. Here, there's the note. I'll put the paper clip on. There, you see, it went down a little bit. Well, that wasn't very convincing, so let's look at a conventional instrument, and you can see on a cello, for example, the high wires, the thin wires give high notes, and the heavy wires give the low notes. So the heavier the wires are, the lower it is. Now, what's the next thing? The length. This says the frequency depends on 1 over twice the length. So if I shorten the length, that will increase the frequency. So the best way to shorten the length is to stick a piece of metal in the way, and then the wave, instead of going all the way up to that end and back and rattling the gourd, it'll only go halfway up and back. And therefore, it'll get up and then down there much quicker. So it'll rattle it about double the frequency. If I get it just in the middle, half the length, and it doubles the frequency, and it sounds an octave higher. And then if I shorten it even further, it should go higher and higher. You see, and this is why on a cello, if you want to play a higher note, you put your finger on, and that stops the wave going all the way up. And that's why it's called stops, if you've wondered why a cello should have stops. Okay, so that shows that this theorem certainly seems to be experimentally true. Now, what's next? Oh, yes, I want to check the speed on this machine again because it's so pretty, but I need a volunteer to help me. Okay, how about, yes. Oh, well, I asked this, yes, you. All right, you can come the next time. Okay. What's your name? Ruth. Okay, Ruth, you get that end, and we will clip that back so that you have it. Now, what we're going to do is to send a wave from each end and see who arrives at the first. They should arrive at the same time, but you have a little practice. Send a little wave, just go up and then down to the middle position again. That's right. Now send a slightly bigger one. That's a beautiful one. Okay, I'll catch it. Now, what we'll do is when I say ready, steady, go, we'll send waves at the same time. Ready, steady, go. Now they're going together, and then they go through one another and come back. And then they're going back. Now, of course, at first you don't know whether they actually go through one another or whether they bounce off one another. So this time, while you send one little wave, quite a nice little wave. No, wait a sec. Wait until I say go. I'll catch it. When I say go, you send one, and I'll send two. And then if they're reflected, my two will come back to me. If they go through each other, then my two should get to you. All right. Ready, steady, go. There, my two. They've got along to you. Now that was pretty amazing. How do waves actually manage to go through each other? Well, the answer is they don't really go through each other. What's happening is you're adding waves. You see, supposing at a certain time, and this particular bar, my wave says that bar should raise 3 inches, and at the same time, Ruth's wave said that bar should raise 2 inches, then the sum of our two waves together said that bar should raise 5 inches. See, and that's how you add waves. Well, before our two waves met, it was very easy because mine was just here and Ruth was over there, and we're adding them together, there was no problem. And when they had passed each other, again, the addition was no problem. It was only when they were in the middle that the addition got all muddled up and looked complicated. And so the waves don't actually pass through each other, they're merely adding all the time. Good. Thank you very much, Ruth. Well, now, the next thing I want to illustrate is the concept of a reflection. I fixed Ruth's end, so I want to send a little wave up like that. And I want to see what happens when it gets to the other end. It just reflects back. And that's, of course, what happens on the berimbau. When it gets to the end, it just reflects back, and it just goes back and forth at 100 times a second. And now I want to illustrate what I actually do. I do to the berimbau. I actually bang it in the middle. So I'll fix this end now, because both ends of the berimbau are tied, and I'll do a down in the middle to simulate what I actually do to the berimbau. It's about here. I do it about 1/3. So what happens, you've got two waves. This one's reflected, then that one goes that end reflected, then they cross one another, and this one comes along here. Now that's reflected. It's coming to this end, and it's reflected. Now they cross one another, and so forth. And so you get two waves going opposite directions, backwards and forwards, like that. So that's actually what happens when I bang the berimbau. Now, there are some rather special waves I want to illustrate, and these are called harmonics. A harmonic is when the whole string goes up into a smooth curve and then goes down into that dotted yellow position, then up to the red position, goes up and down there. And that's called the first harmonic and sounds like the note that we've been talking about, the fundamental note. Now, the second harmonic, the middle point in the string is absolutely motionless. And this end of the string goes up and down like a half-size version of the first one, and similarly that half of the string goes up and down. That's called the second harmonic. And that sounds an octave higher because it's just like this a string of half the length going, plus another string of half the length. Now, the third harmonic has two nodes, one at the third point and one at the 2/3 point. That sounds about an octave and a half above. And the fourth harmonic has three nodes, one in the middle and two at the quarter, and that sounds an octave plus an octave, so that sounds 2 octaves higher. Now, of course, you can make harmonics loud and soft. For example, this middle shape is the third harmonic, but if I want to make it really loud, I increase the height of the string, and so I express that by saying twice the third harmonic. And if I want to make it soft, I reduce the height, and I express that by saying half the third harmonic. And so, of course, you can multiply harmonics by any number to make them as loud or soft as you please. Now we set up a piece of string here. It's connected to a tuning fork here, which is vibrating, and the tension is given by a weight there. And with a bit of luck then, if we've got the tuning fork and the weight right, it should oscillate at a harmonic. Ah, there she goes. Now, you can see what it is. There's a node, and there's a node, so this is the third harmonic. And since this is motionless, I might as well hold it. what's happened is it's stopped any energy getting to the left-hand side, so the string from here to the tuning fork is now operating with the second harmonic. Or I might as well stop it here, and that'll stop any energy getting past, and so now from my finger to the tuning fork is operating with the first harmonic, the fundamental. Thanks very much. Well, now, what is the connection between those waves, which just seem to be going up and down, and all the other waves we had before, which seem to be traveling along? I mean, is there a connection? So what I'll do now is to send a steady stream of waves going in that direction, and you watch carefully what happens when they get to that direction and start coming back to me. See, they've got to the other end now, and they're starting a reflection. They're coming back to this end, and finally, all the travel has disappeared. We've got just a standing wave, just going up and down. Now, if I speed it up slightly, you can see them traveling again. But now you understand what a harmonic is. It's the sum of two equal and opposite waves going in opposite directions, but they add together to give just an up and down wave. Well, now I've come to the crux of today's lecture, and this is a theorem, the harmonic theorem of Fourier. See, this theorem says, let's see what the theorem says. Any motion of the wire is a sum of harmonics. Here, M is any given motion of the wire, and here, H1, H2, and H3 are the harmonics, and these X's are numbers multiplying their loudness or softness. So it says any motion is some number times H1 plus some number times H2 plus some number times H3 plus all the way to infinity. Now, this is an astonishing theorem, because when Daniel Bernoulli first conjectured it in 1753, the other famous mathematicians at that time, who were experts on waves, such as D'Alembert and Euler, said it's nonsense. I mean, you just haven't got enough richness with the harmonics to express all possible motions. And when you think of all the motions that you could possibly put on that wave machine, compared with those very simple special pictures. And they said, a wave is a continuous thing behaving continuously. How can it possibly go into this discrete harmonics? How could it behave so discretely? And so there was a big furore for 50 years until Fourier came along in 1807, and he showed how, given M, it was possible to work out these corresponding X's. And his advance was so great that today we call such series Fourier series. But he didn't prove the fact that if you started with M and calculated the X's, and then you add them all up, then you would get back to M again. We had to wait another 20 years for Dirichlet in 1829, who finally put the last T and dot to the theorem that this was an equal sign. And his paper in 1829 is a beautiful classic, which marks perhaps the beginning of modern analysis. Well, this theorem is in a certain sense a watershed, because up till now, in our talk, we have been talking about physics and waves, and from now on we're going to talk about music, because in this theorem here, this M is really the physics, but these X's are really what we actually hear, because you remember I said the ear was a resonator, and therefore the ear can sort out these H1, H2, and send the numbers X1 and X2 and X3 to the brain. So although the physics plays an M, what the ear actually hears is the X's given by the harmonic theorem. So we should be able to, of course, if you play any musical instrument, you will hear a whole mixture of these, and different musical instruments will give different proportions of X's. But if you still play this one, you will always hear this note, but these other X's will influence it slightly and give a different quality to the note. And that is responsible for the different timbre of different instruments, just different proportions of the X's. But of course, if you take away the first harmonic, then you will no longer hear the fundamental note, you'll hear something an octave higher. And I can do a trick that, you see. Let's go back to these harmonics here. If you play a note, but if I rest my finger rest gently on the middle of the string, then I'll stop the first harmonic, and you only hear the second harmonic, so it should go up an octave. And if I rest my finger slightly on the 1/3 point, I'll kill both the first two, and it should go up about an octave and a half. And similarly, if I rest my finger on the quarter position, you should go up 2 octaves. So now I'll try this. I'm not a very good cello player, I assure you, and so you may hear the most frightful screeches, but let's just try. We'll start with the fundamental. It went up an octave because I rested my fingernail on the middle. Now the third harmonic went up an octave and a half. Ooh, pretty terrible. That was the fourth. Now try the fifth. Ooh, no. You can see I'm no cellist. Now, where's that big caption board? You see, what we've done so far is we have a scale now. This is a scale of the different frequencies. You see, here is the fundamental, and double that you get an octave higher, and treble that you get the next one, and quadruple and so on. And this is really a scale in which the top row is physics, here, which tells you the frequency, and the bottom row is music, which tells you the pitch. You see, because if I look at the bottom row now, I've got the middle C, and then C an octave higher, and then C 2 octaves higher, and then the 8th harmonic, which is 2 cubed, is 3 octaves higher. Well, now, this is a very nice scale for the physicists because all the multiples of the frequency are all equal. But it's a very bad scale for the musician because, as you can see, the distance of the octaves is getting bigger and bigger. And a musician likes to think of octaves as all the same length. You see, so we've got to patch up this scale somehow. We want to stretch out this end of the scale a bit in order to make that octave down there the same length as this octave. See, at the moment, you've got a nice, straightforward scale for the physicist, but an exponentially increasing scale for the musician. So what we want to do is to make it a nice, even musician scale. So, Crispin, would you come and hold that, and Cheska hold that, and pull it out into a musician scale. Okay? Oopsie, we've torn it a bit. There. Now, you see what's happened is the musician has a nice scale where his octaves are all equal, but the poor old physicist has now, instead of having an equal scale, he's got a shrinking logarithmic scale, like a slide rule. Now, so, in order to understand music, if we want to put the physics into the music, what we really need is a slide rule. And we have one. Here it is. You see, this is an ordinary slide rule where you can move the middle part out. Now, the fixed part of the slide rule is going to be the musician's scale. And here's middle C, and here's octave above, C1, and there's 2 octaves above, 3 octaves above. See? And our problem is to know what notes to put in between. And, of course, I've put down here the crazy pattern that you usually see on a piano. You know, white, black, white, black, white, black, white, black. No, that's wrong, isn't it? Well, anyway, the crazy pattern that you happen to see on a piano. But we know that the only natural thing that will sound correct will be this ear. This is our ear, the sliding bit of the slide rule, see? So we can tell whether a thing will sound correct or not is whether or not it comes from the sliding part of the slide rule. And of course, over the centuries and over different customs, there's been a tremendous number of different choices of what scales in different countries. And so now we want to understand why those choices have occurred. So the first thing to do is to find out what the different intervals from 1 to 2, from 2 to 3, 3 to 4 sound like. So I need a volunteer. Now, I promised I'd give it to you, didn't I? So what we want to come round here, stand here. What's your name?
Isabella.
Isabella, same as Isabel here. Now, so what we want to do is to hear the chord. So each time we have a chord, I want you to first play the first note like this, see? So we can hear the chord. So try it on the octave. The octave is from 1 to 2. Very good. Only keep it going so that...
Yeah.
Yes. Now we'll move it along and try and see what 2 to 3 sounds like. Just a bit, wait. Now, well, wait a sec. I'll draw the line down to 3. We'll mark against 3 here. And rip off the paper, and lo and behold, we've got G. So try playing C and G. Very good. That's a fifth. Now, why is it called a fifth? Well, because in our crazy system, there are 5 white notes, 1, 2, 3, 4, 5. So if you start with C and end with G, there are 5 white notes. But as yet, we can't call it fifth. All we can call it is a 2-3 interval. Okay, move the slide rule down. Let's try the next one. 3, 4. I'll mark that. Rip it off. F. Try that. That's what we call a fourth. Why do we call it a fourth?
Because there are 4 notes in between.
That's right, not in between, starting there. 1, 2, 3, 4. That's right. Okay, move it down 1. Now 4 to 5. This one, I've marked this interval red, so I'll put a red note here. Rip it off. It's E, so try that. We call that a major third. Why is it called a third?
Because there are 3 notes.
1, 2, 3, that's right. Yes. Now move it down 1. 5 to 6. Step back a bit. Just on a bit. That's okay. That's perfect. We must get things precise. So we will now put a thing there. And this time we land on a black note. So try it. That's right. That's a minor third. Well, thank you very much, Isabella. So you can see that we're already beginning to build up parts of the scale. But why now do we choose 12 notes, 12 semitones on our scale? And the answer is that G is approximately 7/12 of the way up, F is approximately 5/12, E is approximately 4/12, and this black note, E flat, is approximately 3/12. But they're not really 3/12, and so, for example, let's look at G. You see, if we want to work out exactly the distance up to G, the whole length of the slide rule from 1 to 2 is log 2. I mean, from 1 to 2 is log 2. You see, and from 1 to 3 is log 3. And so this interval between 2 and 3 is log 3 minus log 2. So to get the right proportion that C to G is of the whole octave, we have to take log 3 minus log 2 over log 2. And that's an irrational number, about 0.585. And 7/12 is about 0.583. It's a rational number, but the difference between these two is only about 2 in 500, and so you hardly hear it. Now, these notes, E, F, and E flat, are much further out, and you certainly can hear these. However, following Bach, he suggested we should divide the octave into 12 semitones, and then all the notes would be slightly out, but nevertheless, we could then play in any key at all. And so his great achievement was to write these 48 preludes and fugues. There were 4 in each of the 12 possible keys, and then in order to play them, everybody had to tune their keyboards to equal temperament, and we've been doing it ever since. But if you've got a finely pitched ear, you can hear that it's wrong, and if you're going to just sing a melody, it is much better to sing the true notes rather than these approximations. And if you go to primitive societies where they don't have complicated instruments and don't want to use the harmony, their ballads and airs and music would use much simpler scales. So supposing then we're purists and we want to hear the true intervals rather than these approximate ones, what would we do? Well, supposing then we say we're only going to use the interval from 2 to 3. Already we've built up F and G because this is called a fifth, because F is a fifth down and G is a fifth up. So let's go up another couple of fifths from G. Okay, so we have to put 2 here, and then we mark, but that's above our octave, so let's bring it down an octave, so put 2 up there, back a bit, and bring, now we bring it down an octave, and lo and behold, we've got D. We must cover up E, because that's a thing that we got from the major third. And now we're going to go a fifth above D, so from D, put 2 there, and work up to here. So we've got a fifth up, rip it off, and we have A. Now we've built up a scale of 5 notes. I'll say how I did it. I went down a fifth from C to F, and from C I went up a fifth to G, up a fifth to D, and then up a fifth to A. So we've just got these notes, C, D. So there's only 5 different notes. And what tunes could you possibly play just using 5 different notes? Well, I'll play a few for you. Here's another one. Here's another one. Here's another one you may have heard recently. I had to go down that last time because it's only an inch long, and so it's only got a range of 1 octave, you see. Now, there's an amusing fact that these 5 notes, if you transpose them all up a semitone, then you just get the black notes on the piano. I put a couple of black notes on the end here, on the end of the scale. So that is why you can play a lot of the Scotch airs and ballads on just the black notes of the piano. When I was your age, I thought the Scots were a most perverse race for composing all their music on the black notes when they had all the white notes available. Well, if you're a great artist and you obey rules, then sooner or later there comes the occasion when you want to break the rules. You remember Veneziano, when he wanted to paint that miracle of St. Zenobius, he deliberately broke the rules of perspective. Well, so the composer of Loch Lomond broke the rules in order to, for artistic necessity. He broke out of the pentatonic scale. So I want to explain Loch Lomond. You remember the words, "Oh, you take the high road and I'll take the low road and I'll be in Scotland afore you, and me and my true love will never meet again on the bonny, bonny banks of Loch Lomond." Well, the key word is never, because if you leave that out, "For me and my true love will meet again on the bonny, bonny banks of Loch Lomond." You see, it'll be a nice, happy song. So he writes the whole song in the cheerful pentatonic mode, these 5 notes, and when he gets to the word never, he breaks out. So now I'll play that on the organ, and you will see, when I get to the word never, I will have to use one of the white notes. You can play it entirely on the black notes, except for this one white note. As he's broken out. Well, after these 5 notes, we really want to get up to our major scale. So we've got these 5 notes, and now I'll put back this red note, which I got from the major third, and that gives me E. And the next most important note, of course, in the whole scale is G. So let me put up another major third from G. So could we move the slide rule to putting 4 here? That's right. And so we'll just now put up another major third. And now we've built up the whole, that gives us B, so we've built up the whole major scale. And that's just using the interval 2-3, the 5th, and the interval 4-5, the major third. Now, if we want to be sad, instead of the major third 4-5, we use the minor third 5-6. So let's build up that. We've done the minor third from C to D, so we'll cross out that major third. Now we'll have the minor third from F. We've got to put 5 here. So we'll put a 1 there. And now the minor third up from G. That gives us a point there. And so with those minor changes, we now have the descending minor melodic. Oh, I'll play it properly. See, and so in that way, you can build up your whole scales. Now, I think the next thing we want to do is to play some chords. So, could we push it to 3? So what we're going to do now is to play the chord which consists of all the notes in the octave that we see. So in this case, it's just 2, 3, and 4. So let's play the chord 2, 3, 4. That's quite a nice, mediumly rich-sounding chord. But if we push it that way, towards Crispin, it always gets richer. So now let's try. This says it's 3, 4, 5, 6. Okay, Lou. So there's a nice chord of F major. Well, let's get a bit richer. Push 4 there. So 4, 5, 6, 7. Okay. Ah, but now we're stuck. You see, there's nothing under the 7th harmonic. I'll put a red mark there now. See, the 7th harmonic isn't on our Western keyboards. It sits exactly between A and A sharp, about 2/3 of the way up. So it's about 1/3 from A sharp and 2/3 from A. So this is what's missing from our ordinary pianos. Of course, we can approximate it by playing A sharp. So, okay, let's play A sharp instead, Lou. See, that's a lovely dominant seventh. But there's a little bit of a discord because it's wrong on that seventh harmonic. You see, and therefore you can never finish a piece of music with it. So what we have to do is to sweeten it up. So that means pushing the slide rule towards Francesca. Okay? You see, that's how you resolve you always resolve a discord by pushing the slide rule to the right. So now we'll play the dominant seventh followed by its resolution. Okay? The dominant seventh, resolution. Thanks, Lou. Well, now I'd like to play you a Christmas carol, and I want you to listen very, very carefully because there's something wrong with it. Did you hear what was wrong?
When you played a double sort of.
Good try. Go on.
When you played on Isabel, you had 3 or 4 notes.
Did I? Did I? I didn't notice that. Thanks. Well, anyway, I'll explain what I think is wrong with a tune. You see, on this ocarina, there are, which is, by the way, this is made by John Langley, who lives in Norfolk, and it's based on pre-Columbian bird whistles. You can do bird song. And it's only got 4 finger holes, and therefore the possible fingerings are 2 to the 4th, which is 16 notes. Now, you can get, of the 13 notes here, you can get 11 of them, and that leaves 5 over. And one of these 5 notes is actually very close to this missing 7th. So instead of playing A, I'm going to use this missing note. So here's a plan which shows you where the notes are actually situated. See, this is the well-tempered scale that we use since Bach. G, A flat, A, B flat, B, and C. And they're all equal intervals. Now, these are the notes I'm going to use on the ocarina. G is right, but A is way up, half a semitone higher than normal, because I'm using this odd fingering, and very close to the 7th harmonic, which is represented by that red dot. And therefore, this interval from G to A is a great ugly, large-sized tone and a quarter. You listen to it. It's much larger than a tone. Now, meanwhile, the B is pushed up so that it's about 1/3 of the way up the semitone from B to C. So I've got a tiny little semitone at the top there, only 2/3 of a normal-sized semitone. So I'll play that. Can you hear? It's much smaller than a semitone. Now, that Christmas carol, when you start, the first Noel, the angels did say, was to certain poor shepherds in fields as... You see, it goes skating up and down those 3 notes. So I'm playing this traditional carol, which was written well before the Bach wrote his well-tempered clavichord in 1722, and therefore it's quite likely to be a carol which was based on people singing, using natural intervals that they heard with their ear. So when I play it again, now listen very carefully, and you will see that I'm using these very odd notes and see whether it sounds right or not. Thank you. That's going to be very well. Minute and a half early.